In section 10.2, we conducted a hypothesis test for a single proportion. We had one sample and we used that to test whether the population proportion that we thought was true was actually true. All right, now we're going to do that same process again with all those steps, but we're going to do it for a population mean this time. Now we have all these requirements up here, which should look familiar because those are from section 8.1, the central limit theorem for the means this time, not for proportions. We have our hypotheses that we have to create, which look very familiar, very similar to those from 10.1 or 10.2, excuse me. Alpha, the test statistic. We've already practiced in the first example finding these critical values if we have to do the classical method, and so on. Now remember, you don't have to memorize any of this. All this is on your exam notes packet. So let me pull that up real quick. There, it's all right here in the appendix, and this is given to you when you go to take your tests. So you don't have to bring your copy, they will have a copy there for you. There's no need to memorize any of this. You just have to know how to use it and what's going on and be able to interpret it. All right, speaking of which, we are going to interpret it for a particular problem. So we're going to scooch past the critical value question, which we've already answered, and we're going to move on to one where we actually have to conduct a hypothesis test. So according to the United States Mint, quarters have a mass of 5.72 grams. Researchers interested in determining whether the new state quarters, which are not so new anymore, but they were new a while ago, have a mass that is different than the old value of 5.72 grams. He randomly selects 18 state quarters and measures them and obtains the following data. One assumes these are the masses of those 18 different quarters. So the first question that's being asked is, are each of the requirements for conducting a hypothesis test satisfied? Well, in other words, what I'm asking is, have you met the conditions of the central limit theorem? And those conditions are right here at the top of the appendix. They're also at the top of that page, a couple pages ago in the notes. It has the full test rundown, and the requirements are up here. It's the central limit theorem for means. That's what you want to meet, which is section 8.1. So I'm going to copy these and paste them into my notes, and then I'm going to type them up. 1 second. All right, let's start with the first condition, which is almost always the easiest condition. Matter of fact, always the easiest condition, because it's going to be given to us. We basically cannot do anything in this class without having without having a random sample. That's why the word randomly is featured prominently right there in the write-up, and it has to be that way. We are not capable at an undergraduate level at all of dealing with non-random samples. It's really, really tricky stuff and sometimes impossible to deal with, at least mathematically speaking. All right, now an independent sample. So this is really interesting. If we're sampling without replacement, so that means without replacement is a problem for us, right? I get students sometimes they'll say, yes, sampling without replacement. No, that's not an answer, right? So it's if you're sampling without replacement, then you've got to watch out. If you're sampling with replacement, like dice and coins and stuff, then you don't have to worry at all. So we are sampling with replacement, so we have to be concerned. So we are sampling without replacement, so we have to make this argument here. So little n is, so is little n less than or equal to 0.05 capital N? Well, little n is the sample size, which was 18. And that capital N is all the state quarters made. So this gets a little, of course it is, right? So we kind of we wave our hands at this a little bit. So we make a little logical argument here and we say, okay, little n was 18, capital N was all the state quarters ever made. Of course 18 is less than 5% of all of those. That's just silly. A cleaner way to write this for my students in class, they'll sometimes say this, 0.05, and then for capital N, they'll actually just put in all the state quarters made, right? So that way you're letting me know that you know what your sample size was and you know what your population size was referring to. So that's another way to do it. When you want to write this, you want to make sure that you're clear on what capital N is and what little n is. A lot of students will just write, yep, that little n is less than 0.05 capital N, but unless you actually write down what it is for this context, you're not really showing the instructor that you know what the heck you're talking about. So you want to make a little logical argument and just say kind of course it is, right here. There, that's a much cleaner way to write it. And that's the way most of my students in a face-to-face class write it as well. So they'll say the little sample size less or equal to 0.05, and then they'll write out what capital N is. Remember, that's your population size. And then just say, well, of course it is. I actually have some students saying, duh, of course, to quote Homer Simpson or Bart Simpson. All right, now whether the distribution is normal, well, that's a little bit trickier. So we would need n to be bigger than 30 or for it to be given to us in a graph. Well, obviously our sample size is not bigger than 30. We only have a sample size of 18. So we need to have it given to us either written in the instructions somewhere that it's given or using the graph. Well, we were given a graph this time, and the graph is the normal probability plots that we know and love from section 7.3. And indeed, it shows that the distribution is normal. So the graph reveals that the data were normally distributed, since the points follow a linear pattern. See section 7.3 when we first learned about this.